Okay, so picking up from where we were last time, so recall we have this point of view on, when you're using the polar coordinates conversion formulas as a change of variables function, and that kind of always going down sort of pretty much the same way. There's all sorts of little streamlining conveniences that we can take advantage of. One is we already know the stretching factor. We've memorized the stretching factor. That's R. And the other is that we have so much experience with polar coordinates, we can just straight up see what R and theta slices look like. Without actually looking in the r theta plane, we can just look and see what they look like right there in xy space. It's just immediately observable once you make this recognition. So we did several examples of that last time. The segue that I'm taking advantage of here is that the exact same thing happens in cylindrical coordinates. So again, we know the stretching factor. We computed that. Again, R. I mean, polar and cylindrical really do have a tremendous amount in common, right? But again, we can see what the slices look like, right? Perpendicular to the theta axis. Yeah. Oh, I made a bad color choice there. Perpendicular to the theta axis in r theta z space, right? These slices, they look like that. Well, yeah, I know exactly what those look like in x, y, z space. They look kind of like this. They're what I like to call half planes hinged on the z-axis, as if they're like, imagine a little door where the hinges are literally on the z-axis, and these theta slices, as theta changes, just kind of like a door, just kind of swing around that axis. Okay, so having made that observation, a couple of little quick tips and tricks. Again, you don't have to consider all 6 possible orderings of your differentials. Practically always, and I suppose there might be some weird, highly manufactured examples to the contrary, but by and large, these are your 2 options, right? There's hardly any reason to entertain any other option. The way you remember what these options are is that the r and the theta are always together and in the usual order. And so then the question is simply, is the dz on the outside of the dr d theta or on the inside of the dr d theta? And how you choose between these, you could probably guess. It's largely a question of what's more naturally and conveniently viewed as a function of which other, right? And so if you are given z as a function of r, for example, you'd probably want to pick this one on the right. And if you're given r as a function of z, you'd probably want to pick this one on the left, right? Okay. So that's a nice little streamlining there. Likewise, it's so easy to forget the stretching factor. We've got so much geometry going on in the slicing process. It's easy to just forget, just straight up, oops, right? And again, it's a big point. It's arguably the big multivariable calculus idea of an integral in cylindrical coordinates question, is accounting for the stretching factor of the differential volumes. So it's worth points. Get those points, right? Make sure to get them. And the way you make sure to do that, I think, is to write down the entire r dr d theta dz all at once, all at the same time. Don't trust yourself to remember that stretching factor later. You'll never need dr d theta dz without the r. Why would you ever write it down without the r? It's just it's a bad strategy. Okay, all right. So let's see a couple of examples, or said differently, the same example twice. I'm going to consider the upper half ball of radius a, like this. This solid here, and we've got some triple integral on this for whatever reason. Again, you could imagine doing this in rectangular coordinates. It's going to have square roots everywhere. Lots and lots and lots of square roots. Okay, all right. So instead, let's do our slicing in this order right here. Arbitrarily, just to get the ball rolling, dz on the inside, dr d theta on the outside. And yeah, let's slice it up and see what happens. Starting with theta. Loosely speaking, our first theta slice is going to look like this. And then theta kind of goes all the way around. And our last theta slice, right back where we started in some sense, but of course, having gone all the way around, theta goes from 0 to 2 pi, just like in polar. Okay. Alrighty, so next we're going to fix a value of theta and thus focus our attention on this one theta slice. Next question, we're going to look at r. What's the range of values of r here? Now, reminder, we're not interested in the solid anymore. We'll get the whole solid for various different thetas. We are interested in how the r bounds depend on theta, so we look only at one arbitrary theta slice at a time. Right? So on this theta slice, my r slices, constant value of r, of course, is a cylinder. And if you think about how that r slice intersects with our existing theta slice, then of course all we get is little sort of line segments, kind of like that. So this is all we're actually interested in. And those r slices, well, they start here, where r is clearly 0, and they end here. Now we do have to do a little bit of thinking about this ending slice. This ending slice happens at a point, you've got to think about the geometry here, right? But it happens at a point in the xy plane, and that means that the radius of the sphere is also going to be the r coordinate for that point. And that, again, you've got to use the geometry. Again, that means you have to have a good picture. Right? So at that point, r is a. Is everybody on board? Okay, and now, as per usual, with both r and theta fixed, thus looking only at my r slice of my theta slice, we now proceed to the next most inside bounds. That's z, and of course z starts here, and pretty easy to see that's where z is equal to 0. Right? And then z is going to end here. Now, again, you're going to have to do a little thinking on this one. That point that represents my last z slice, that's going to give me my upper z bound. That point is on this surface. Again, credit the picture for telling us that, right? It's not because we haven't used that algebra yet and it kind of feels like it ought to stick in there somewhere. No, the picture is what tells us specifically that that point is on that surface. And, of course, being on the sphere that has that equation, right, cylindrical equation, that is, right? Now we have to solve for, wait a second, it's really easy to lose track of what we're doing here. I'm looking for a z bound. And so in this equation, I need to solve for z. And that, then, is my upper z bound. Everybody see the process? Note the analogy. Note how mechanically, in some sense, it's just like rectangular triple integrals. It's just that the slices are a different shape. And the equations are equations of different variables. Other than that, morally kind of the same. Okay, so that's one way to do it. Now, we could slice in the other order. Same domain, right? Not changing the domain, same exact question. We're just going to do it the other way. This time we're going to put the dr d theta on the inside and the dz on the outside. Now we get a totally different slicing sort of process, right? Here we start with our z slices. Of course, z slices we've talked about with rectangular coordinates. Z is literally the same coordinate, so the z slices look exactly the same. Right? And you can see those z slices that look like this. They kind of start down here where z is obviously 0. They end up here at the, North Pole, if you will, where Z is, if you think about it, one of our radii of our sphere, and thus Z is A. Yeah? Okay. All right, now, again, following our usual process, we're going to fix a value of, why am I in red? That's so stressful. Z here. Right, looking at a given Z slice. Now I got to think about what's the corresponding range of values of theta. Again, only on my Z slice. Forget about the rest of the solid. We'll get to the rest of the solid for different values of Z, which will range over all of what we need. We'll get there, right? But one slice at a time. Theta. Here's kind of my first theta slice, and it just kind of goes all the way around. So, very often this is the case. Not always. I emphasize not always, but it's not rare for the theta bounds to, if theta goes all the way around, you can just write down 0 to 2 pi. Right? Nice convenience. Now, as usual, now we focus on given fixed values of theta and z, thus giving us that as our theta slice of our z slice, and the usual game proceeds. Where is r going to start? Well, r starts there, where r is, of course, 0. And r is going to end here at that point. And again, got to think it through. That point, what does the picture tell me? That point, let me get rid of the mess. That point is on the sphere again. Same equation. But very importantly, don't forget to recognize that we are looking for an upper bound for r here. So I need to solve this time for r, not z. Like up here we solved for z because we were looking for a z bound. Down here we're looking for r. So we solve for r, and that then is our r upper bound. Everybody good? So again, the pattern, the slicing process looks different depending on whether you put the the DZ on the outside or the inside, but it's this general structure of the process is all kind of the same. Okay, so, and likewise in spherical coordinates. Again, it's a change of variables function. Again, it's a pullback. Again, we know the stretching factor, right? Rho squared sine phi. Make sure to have that memorized. Rho squared sine phi. And again, we could pull back and talk about, theta slices, and we could talk about phi slices. All of that in rho phi theta space, but that's actually really pretty challenging geometrically. These spherical pullbacks can be pretty rough. So it's much more convenient to just think about, well, what does a constant value of, for example, theta, what does a constant value of theta look like in XYZ space? And it's just like with cylindrical. It's always a half plane hinged on the z-axis. Right? And then likewise for the rest of these. Now here's the bad news. The bad news is constant values of phi. If you think about what phi is, phi measures angle off of the z-axis. So a constant value of phi is a cone, which is weird. And, we talk about these things as being slices because we imagine, cutting with a knife. And I don't know any knives that make cuts that shape. So this is geometrically weird, right? A little hard to relate to, granted. There's some good news coming up in a moment. Even worse for rho, if you look at a constant value of rho, right? Well, oh gosh, right? That's a sphere, right? So really not familiar with knives that cut in that shape. So bad news. But here's the good news. Good news is, in practically all cases, you want to slice in this order. D rho, d phi, d theta. practically all cases. There are cases where it's just as good to go in another order, but there are very few, if any, naturally arising cases where a different order than this is actually better. It's practically unheard of, right? So just make the plan. Just always go in this order right here, d rho, d phi, d theta. And here's why that's really good. If you look back to these slices, a theta slice is easy to draw, easy to visualize. Now, phi slices are weird, but keeping in mind that I don't need to actually think about the whole phi slice. I only have to think about what a phi slice looks like on a theta slice. Straight line, right? The way this cone intersects this plane, it's just a line. I guess a ray. Right? So, sweet. And then thinking about the different values of rho. Yeah, again, that's weird and hard to draw and hard to visualize, but you don't need to really imagine that whole thing. You just need to imagine how those intersect on this phi slice of this theta slice, and so that works out to be pretty easy. It's just imagining the values of rho increasing as you move along that line. So the slicing process in spherical, if you make the clever, ideal choice of which way to do your slicing, it's not that bad, right? So always that order. Same other little bits of advice here. Please, please, please don't forget the stretching factor. It's so easy to forget. Oh my God, it happens all the time, and it's tragic because it's leaving money on the table. That's worth points, sometimes as much as 5 points, just for having the stretching factor correctly inserted into the integral. Get those points. Write all this down together. Don't ever write down d rho, d phi, d theta by itself. You'll never need that. It never comes out. It's always part of rho squared sine phi d rho, d phi, d theta. Write it down all at once. Okay. All right, and again, the usual process of how to find bounds. So most of the challenge with these is geometry. Drawing the pictures and thinking, interpreting the pictures correctly, and, drawing your slices and this kind of thing. So here we go. Let's see here. So we are going to consider here a ball, radius A, not centered at the origin, centered above the origin at A on the z-axis, right? So this is what I have pictured here. Suppose this is our domain. Now, let's, again, think about our alternatives. I mean, if I did this in rectangular coordinates, square roots everywhere. It's a nightmare. Okay, right? Well, what do theta slices look like? Now, this is what a generic theta slice looks like. A half plane hinged off the z-axis, and the way that intersects with our ball is about like that. And how many of those do we get as we sort of swing around? And well, it goes all the way around. So 0 to 2 pi. And we're already making progress. Everybody good? Okay. All right, so as usual, we think about a particular theta slice. On this theta slice in this theta half plane, we have to think about the range of values of phi. Right? Looking at the order that we are going to go. Right, we did our theta, and next is phi. So, okay, we're going to have to imagine phi slices on this theta slice. Now you can just do that right on this picture. That's totally fine if you want to. I have a slight preference myself. This is just to help me think about the geometry. You don't have to do this. I think this is a neat trick, and that is go ahead and redraw that theta slice. So there's my theta half plane. Here's my theta slice on that theta half plane, right? And now notice let's see, for example, this, which is a right angle, but doesn't look like a right angle. That little perspective problem just waiting to confuse you, right? Because of three-dimensional pictures on two-dimensional paper are just awkward and unnatural, right? Not a problem over here. Over here, that right angle looks like a right angle, right? So I think that's confusing, and I think this is easier. Again, it's not required. You don't have to do this little redraw, but I think it's helpful, and I think you'll be less confused if you do that little trick. So with that in mind, looking now at our theta slice, let me draw this again. There's our theta slice. Here are our phi slices. They start at phi equals 0. Right? A generic phi slice going to be kind of like that. And then our last, now you got to kind of, this is geometrically tricky, but you have to think about how do these phi slices, as you proceed along, where's the last one? And I feel like the last one is going to be straight horizontal, pi over 2. And again, you just have to appreciate the picture on this. The picture is what tells all. You cannot, write down the equation of this thing and somehow infer that from the equation. I mean, you probably could in some extremely careful, laborious, really impractical way. The picture, though, is what really gives us this information. 0 to pi over 2. How we doing? Everybody sold on that? Okay. All right. Okay, and then as usual, we look at our phi slice of our theta slice, and we have to look at these points and think about what rho is doing. So let's, our first value of rho is going to be right there. Now, a quick reminder, that point is, it's really this point over here. Right, let's not lose sight of the fact that we're really on the three-dimensional picture, and we just kind of redrew this for artistic convenience, right? But in fact, we're at that point, which is the origin where rho, of course, is 0. Yeah. And then likewise, our last point, that point right there, it's on this curve. Okay, wait a minute. What is that curve? Let's not forget we're actually over here on the three-dimensional picture. That's that curve. So we're looking at a point on that curve, which in fact is a point that's on the sphere itself. And again, the pictures are what tells the story here. So this point where I need to understand rho, I'm going to have to understand it by way of writing down the equation for the sphere. And now this is a chapter 1 problem, so let me just say yada, 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 but this is the equation of that sphere. Now I just kind of waved my hands at a significant amount of algebra converting a rectangular equation for this sphere that you can just write down from the description using sort of, high school algebra 2 ideas, basically, right? That rectangular equation you then have to convert to this spherical equation. So make sure you can do that algebra. I know it was a long time ago, right? But that's a important part of this process. And reminding ourselves now that the reason we're interested in that point, and thus this equation, is that we're looking for an upper bound for rho. We solve for rho. We got lucky it was already solved for. Isn't that nice? But you have to solve for rho, and there then is your rho bound. Everybody happy? Okay. All right, so that's the process. Again, mechanically, it's a lot like, the only thing that's really different with spherical integrals versus cylindrical versus polar is, the geometry is a little different. But the sort of the structure and the process are basically the same. I do want to give you a pitch here. This is all strategic, frankly, right? But, you've been hearing me preach about how important the picture is for the last couple of lectures, right? And it's just unavoidably critical to have a good picture for a couple of reasons. For one thing, it'll help you understand what's going on. It'll help you see it in your mind, right? It'll tell you which points and which surfaces and therefore which equations. It guides you in the right direction. It's part of getting a right answer. But I emphasize as well, it is also part of communicating your thought process, right? We're not going to be just looking at your answer and seeing if it's right. I have to be able to look at what's on the page and infer what you were thinking. Now, you'll notice I didn't exactly write a paragraph here about my thought process, right? But there's enough on these pictures that it's pretty clear where I got my thetas from, right? Even here, just that little bit of documentation on the picture makes it clear what my reasoning was that got me to my bounds. So it's very important to have a good picture. And with that in mind, how do you make a good picture? Don't make it too small. It's very common for students to, try to squeeze it all into, something like this, and then they draw their slices, and then they have and then like that, and I'm supposed to infer something from what is actually, about that big. Right, so please don't do that. Notice my pictures here are pretty good size, and some of my pictures even bigger. Right, use some space. Don't forget on exams you have the entire back of the page. Right, so if you want to reserve the front of the page for algebra or something, I suppose you could do that. But anyway, one way or the other, make sure you have a nice, big, clear picture. I'll remind you as well that you should not expect that you'd be able to just instantly write down the perfect picture. I know I can't, and I've been practicing this for decades. Right, so you should expect that it might take you a sort of a revision process. So I'm a big believer in the idea of first draw the kind of a first cut at it. Expect your first cut to be not impressive. Right, this would be a great place to use your scratch sheets, and then expect to learn a little from your first picture. Right, it helped you see the shape in your mind better, and then your second picture can be better. And then you'll learn more from that second picture, and then maybe your third picture is what you actually use. Right. So anyway, don't try to just don't try to make your first draft perfect. It's very often not realistic. Last comment. This is not just a matter of natural talent. A lot of people think, oh, I can't draw pictures. Okay, well, you can improve if you understand techniques. There are things to know. There are clever ideas that, when explained, if you digest those clever ideas, that'll help you make better decisions in the drawing process. And of course, don't forget to practice. This is a skill. This is something that takes some doing. It's like dribbling a basketball. You can watch people do it all the time, as we do here, but you got to get your hands on the ball and spend some time with it. Okay. All right. So I put everything that I know about mathematical drawing into those recordings I have on my YouTube channel, and I encourage you to either look at that or look at some other, but definitely get good counsel on what those tricks are. Okay. Another example. Here we have another ball of radius A, this time centered over here on the y-axis instead of the z-axis. And this makes a pretty significant difference in how this plays out, as it turns out. A lot of people would think, what's the difference? Y-axis versus z-axis. And what you have to remember is that in spherical coordinates, the z-axis is special. The z-axis is what the theta slices are hinged on, not the y-axis, right? The z-axis is where phi is measured from, not the y-axis, right? So this one little change actually is going to make a huge difference in how this plays out. Okay, so that said, here is a theta slice. geometric appeal. This ball here, if you're taking a slice through it, by the way, feel free to just get some Play-Doh, right, and make a ball, and then take a little knife and you can just literally cut it open. Oranges if you don't have Play-Doh, whatever, and you can just use actual physical models and help yourself visualize what these slices look like. In this case, we're going to get a little disc here about like that. And now we have to think first and last. And again, this is a geometric appeal. Our center is at A. Our radius is A. And that means that in some sense the kind of the end over here, right, the farthest to the left point on this sphere is the origin. So this does not encircle the entire z-axis, and theta does not go all the way around. Right? It just barely touches right there. It just kind of side swipes the xz plane, if you will. Right? And with that in mind, I make again the geometric appeal. We just work off the picture here, but our first theta slice that actually hits anything is here, where theta is 0. And then theta only goes about halfway around, and the last slice is over there where theta is equal to pi. So our theta bounds 0 to pi. Got to see it from the picture. How are we doing? Okay, so as usual, now we focus on a given theta slice. Again, I'm going to use this trick where I take my theta slice and I redraw it. I just find it easier to visualize what's going on, looking straight at it as opposed to, trying to look at this sort of askance view that we have on the left there. So looking straight at it, now I can start thinking about phi, and our phi slices look like this, right? Remember, measured off of the z-axis. So phi is this angle, like that. Yeah, everybody good? And so again, you got to think about first and last. And thinking about first and last, this kind of slice, the first one that actually hits anything is straight up. And the last one, oh gosh, is straight down. So 0 to pi is our phi bounds. Is that good? Alrighty. And then, again, as usual, we look at a phi slice of our theta slice. Now we got to think about the range of values of rho. We start at that point, which of course is actually that point, which of course is the origin, where rho is of course 0. Yeah. And we end, let's see here. I'll use orange. We end at that point, which we're going to want to say is on that curve, but that's really this curve. And so when I say a point on that curve, in fact, what I also could say is that's a point on this sphere. So you've got to do a little bit of chapter 1 algebra here. You got to take the equation for the sphere that you can easily write down in rectangular coordinates. You got to convert that to spherical coordinates. Chapter 1 methods, right? Make sure you can do that. I know it was a while ago. Right? By the way, this kind of thing happens. I'll let a quick interjection. This kind of thing happens all the time. But, this is a very vertical class. The stuff that we do early in the course, we're building on top of that, and so usually what we're doing at any given point in the course will be calling back to things from earlier on. So this is not a rare scenario here. And again, we're looking for rho bounds, so we solve for rho. again, already done in this case, got lucky. But anyway, this then is your row upper bound. Is everybody happy? All right. Cool. Okay, moving along. This next example is mostly an art sort of insight. It's really hard to draw this example. So I'm just going to talk about the art. The actual algebra and trig and slicing of it is just like all the other ones that we've done. But here's the artistic challenge. We're looking for what is inside of this sphere, right, because of this less than or equal, and then what is outside, because of that greater than equal, outside the regular unit sphere, right? So outside of the red and inside of the green, and all together then geometric appeal, our actual solid here. And this is what's tough to draw. I mean, I'm going to kind of draw that, but I mean, really, now use your visual imagination. What we actually have is a ball that's had a ball-shaped scoop taken out of it. So imagine, there's an excuse to buy some ice cream, right? Get a bucket of ice cream, get one of those little scoopers that has the little spherical, and take a nice spherical scoop, right? And then take your scoop and then take a spherical scoop out of your spherical scoop. You know what I mean? And when you do that, what you're going to see is there's actually kind of a sort of a lip down here. And so, yeah, there's a bunch of solid up there, but there's a little bit of solid kind of around here. And then in the back, likewise as well. And you see why it's hard to draw, right? It's significantly challenging. It's really hard to work with. Okay, so, and of course, we're going to have to take this hard-to-draw thing, and we're going to have to think about how to take a slice of this hard-to-draw thing, right? So here's the what I think is the artistically important takeaway from this example. First of all, I'm going to use this term intersection to describe our thing here, and keep in mind it's not the intersection of these two balls, right? It's the intersection of the interior of this top ball with the exterior of the bottom ball. I don't know I guess you could call this an exclusion or something. But let's not get bogged down in language. I'm going to call that an intersection, right? And the big idea is that if you're taking cross sections of your intersection, and if that's geometrically hard, which I claim this one is, a cross-section of your intersection, you can just as well think of as being the intersection of the cross-section. Said differently, you can take the cross-sections first. Forget about the intersection, just temporarily, right? Look at the cross-sections themselves, and the cross-section of that top sphere is just a half a disk. That's easy. Right? And you can look at the cross-section of our bottom sphere. That's just another half a disk. That's easy to draw, right? And with those drawn, it's pretty easy to talk about how they intersect. And again, interior of one, exterior of the other, right? So it's pretty easy to see once you've drawn the intersections themselves, once you've drawn the cross-sections themselves, it's pretty easy to see what's left over as they, again, intersect, using that term a little bit. So I just think that's a neat artistic trick. It's much harder, in my mind, to imagine the actual three-dimensional solid and then imagine taking a cut. I find that very confusing. So again, I just wanted to make this artistic observation, right? You can get down to this nice, convenient representation of your theta slice, off of which we do the usual work, and you think about the starting and ending and the points and the solving, and that's all pretty much the same. But we get a nice, easy picture to work on because of this observation right here. Everybody all right with that?
How'd you get 0 to pi over 3?
Yeah, so that's just that's one of these details. Let's see here. So the pi over 3 comes from the fact that this angle is pi over 3, and the reason I know that's pi over 3 is because that is 1 because it's a radius of this circle, and so is that, and this is a whoopsie. Let me get rid of yeah, that's a radius of that, so we have another equilateral triangle situation. Yeah. Okay, so that's spherical coordinates. Okay, so we're going to move along to the next thing. This is, I think, one of the most underappreciated integration techniques that I'm aware of. I'm not saying it's the best. I'm saying it's the most underappreciated. Right? This is an awesome trick. I used this trick that I'm about to show you so much. It saved me an immense amount of work. And I'll try to quantify that a little bit after I show you the trick. But very valuable. The book kind of barely mentions it. Some textbooks don't even mention it at all. I think that's crazy. So here we go. I'm going to start off with the theorem y'all have already seen before. This is a single variable calculus theorem. But if you have an integral where your integrand is odd, meaning that, and if your domain is symmetric, meaning this, now let me write this down, just in practice how you probably saw a domain that is symmetric. You probably saw the bounds as being negative a to a, right? Symmetric in the sense that the upper bound and the lower bound are negatives of each other. So when you find yourself looking at an integral like this with these two conditions satisfied, the integrand is odd, the domain is symmetric, and we get an awesome result, is that that integral is 0. No further calculations required, no integrating, no substitutions, no integration by parts, nothing, just boop, 0, done, walk away. Right? Awesome theorem. Now, it doesn't come up super often in single variable calculus. But you can take different points of view on why this is true. I like the Riemann sum point of view because you can imagine if you're looking at your symmetric domain from negative a to a, and if you imagine slicing this up, you could look at a piece over here for which the corresponding term in the Riemann sum is like that, and you could look at this term over here for which the corresponding term in the Riemann sum is like this, and these are negatives of each other. And so those two terms are going to cancel in the Riemann sum. And because of the symmetry, every, if you will, slice on the left cancels with a corresponding slice on the right, and so poof, puff of smoke, 0. Right? All right. So now there's also a different point of view. You can think about this as a substitution. And don't forget, substitutions are basically change of variables. Right? But if I just let x equals negative u and do the substitution, here's where the substitution happens, aka the change of variables, aka the pullback. And notice all you need is for the domain to be its own reflection, thus the symmetry. And you also, the other thing you need is for the integrand to be, I circled the wrong thing. Sorry, here we go. The integrand to be odd, thus that minus sign. And we're done. Right? We have just shown by this pullback argument that this integral is its own negative. And what value could it possibly be if it is its own negative? There is only one number that is its own negative, and that's 0. And so therefore the integral is 0 as required. It's a lovely little proof, right, using substitutions. All right. So here's the upshot in multivariable. There's a two-dimensional version of this. And it's really, really similar. It's really analogous. The big difference is that we have to reinterpret what symmetry means. It's going to come off of the idea of reflection over a line. Keep in mind, if we have a two-dimensional domain, right, then we're not going to be reflecting points on the line over a point. We're reflecting points in the plane over a line. So this is what a reflection is, and the formula for the reflection is, I'm going to say exactly what you would think it is, just like when you look in the mirror, right? Sort of, you're seeing your reflection perpendicularly to the surface, and equal amount on out the back as from the front, right? So exactly what you think it is. And with this idea of a reflection, we can write down what it means for a function to be odd. Odd means you get a minus sign when you reflect. What does it mean for a domain to be symmetric? There's different ways that you can think about this. I like to think about a domain being symmetric if it is its own reflection. Nice way to, it's, exactly what you would think, I would imagine. Okay, and with those ideas established, great news. Another theorem. It's just like the single variable version. And that is, if you have yourself an integral, and if your integrand is odd, and if your domain is symmetric, then that wrong color. How anticlimactic. That integral is 0. No slicing and dicing, no bounds, no worrying about corners, no integration, no square roots to worry about, right? Just boop, 0. Awesome. Extremely powerful. Now, there are a couple of warnings I have to give. This is a powerful theorem, but it is also a delicate and therefore dangerous theorem. And so you do have to make sure that you're careful with this. You do need both of these theorems to hold. So you need both of the conditions to hold, right? So this is very important, and a lot of students will mess this up, and a lot of students will see a symmetric domain, and then they're like, ooh, symmetry. I'm going to use symmetry. Awesome. This is going to be the greatest. I'm just going to declare this to be 0. If your domain is symmetric, but if your function's not odd, you've got nothing. That's not, half of the conditions is not half as good, right? It's just nothing. So do be careful that you check both of the conditions. And also, you've got to be using the same line for both of these symmetries. That's really, really important. You'll see why in just a second. It's got to be the same line for both of them. So do be very careful about that. But that said, yeah, awesome, powerful theorem. Now, again, you can see this two different ways. There is a change of variables. We pull back through the reflection. And then, knowing that the domain is its own reflection, and knowing that the integrand is odd, and thus that minus sign, then we just got through showing this integral is its own negative. What could possibly be its own negative? Only 0. So the integral has to be 0. And then analogously, here's kind of a Riemann sum point of view. This is, if you don't like the substitution change of variables point of view, if you have a symmetric domain, and this was my attempt to draw a symmetric, generic, symmetric domain, then you're going to have this term in the Riemann sum. You're going to have this term. Oh, whoopsie. You're going to have this term in the Riemann sum. And they're negatives of each other because of the oddness. And the terms therefore cancel. And again, everything disappears in a puff of smoke. So take your favorite point of view on that. And now let's see here real quick how we do it. Oh, and I am out of time. Okay, so you're going to have to sadly wait until after spring break to see an example of this. But this is where we'll pick up. Y'all have a great spring break, and see you in 10 days.